Hi everyone. In this video, we will see what are the indexing options available in Databricks. Unlike other native SQL engines, Databricks doesn't have native indexing options. Rather, it uses file-based options like partitioning, z-ordering, liquid clustering, and Bloom filter. As part of this video, we will see partitioning, z-ordering, and liquid clustering, and we will see why liquid clustering is the best. We'll see how it evolved from partitioning to liquid clustering. So let's create a partition table. So we are creating a partition table for this demo and it is partitioned by country. Now let us do a insert. So I'm inserting some random 100k rows for the sake of this demo. So we are doing a load and I'm loading the data partition by country. So this code will randomly insert some random names and country and it will load the data. See the partition information. So describe extended command can be used to see the partition information. So you will see the column names. Under that you will see a section partition information that will give me the partition column and what is the data type of the column. And additionally I want you to also look on the table properties. So in case of a normal partition table, it will have only the delta versions, which is the protocol used for reading the delta tables. But as we see, when we enable liquid clustering, you will see additional properties which are added. So let us look at the folder structure. So partitioning is a folder based approach. So you will see it's a simple mechanism. In order to narrow down the data, we will create folder for each partition, and for each partition value, say Canada, Germany, India, for each of this, you will see a set of files which will be written according to that partition, right? So if you see here, there are multiple files written. Right? Now let's see how does the delta log folder looks like. So delta log folder is nothing but for each delta table, it internally uses a underscore delta log folder which holds the stats of your or the metadata of actual data. So for each of your commit or each of update in the table, you will see a version created, and each file will be a JSON file. For once in 10 files, it will compress and then create a Parquet file. So since you have two versions here, let us see the two versions. So the very first version is a data creation or table creation, right? So you will not see any data apart from metadata tag. So metadata tag will give you informations like who created the like what was the table, what are the column, what is the partition information, right? So those things will be there. Now when we check the next file, you will see the additional information. So this will have two columns. If you see, add is one of the tag and we have a commit info. Under add tag, for it will give you whether a data change is involved. So data change true means it is rewriting the data, right? In this case we are inserting the data, and partition values will capture under which partitions, right, the data is holded in this commit. So this will help delta to basically, when it goes or when we fire a query on a partition, it doesn't need to scan all the content, it will just use the stats. So if you see here, for this file it holds the min value, max value, count, null count. You could see null count and you could see minimum values and you could see maximum values and the number of records, right? So now when we trigger a query, right, say we want some sample data for country equal to Canada. So in this case, you will see the result is instantaneous, right? That is because it doesn't needs to go and scan all the data. It knows the data is on a particular party, the query is on a particular partition. So you can verify from the scan read that it will read only one of the partitions. So you could see here the number of partitions, number of partitions read. So you could see it is one. Now let's see, let us run a query which involves a count, right? So again this is a count on a partition column. So as you saw earlier, all the partition metadata, right, like the min value, max value, counts will be stored in the stats. So this gives a result instantaneously because it doesn't even need to open a file, right? And now let's see where we want to query by a column that is other than a partition column, right? So now what will happen is it has to read all the partition data, right? Because it doesn't know because this alias name is distributed across partitions, it will take some time, right? Now let's do some other operations. Let us update a partition table and let us see how it works. So any operation such as an update will need an override. So you could see it is saying rewriting files. Now it overwrites the data. Now if we go and see the partition information, if you see, you could see two Canada folders because we updated the name Canada to this Canada. It basically updates the partition and it also rewrites the content of the file. So you could that can be confirmed via delta log. So you will see one more commit file will be added. So now this is the second commit. First is the initial creation, second is the insertion, third is the partition update. So now when we read this partition update commit, you will see both add and remove files in this case, right? Because we have added or basically it copied the original file and we could see the data change is true because it has to copy the data, right? It is not just a metadata update or something. So you will see removed files and you will see add files with the metadata. Now let's see, let us update a value inside the content, right? So when you update a value inside the content, I think it will also involve a rewrite, right? If you see here, it is rewriting the 40 files. It identified 40 files where it had allies. So it is updating that allies with the new name. So you will see it takes some little bit of time because it has to rewrite the entire content of the files. Yes, now it is written. Now we can go and check the third commit. So here you could see it will, if you see here, there are a lot of removals because all the files where there is a word alias is there, those files would have been rewritten. So even for the same Canada partition, you could see multiple files where alias is there and it's all rewriting those files, right? Now let's see what happened when we delete a value. So I'm just deleting a name, right? So even a delete operation, as you guessed, it will involve rewriting because it has to delete all the files where Diana is present and then create a new file without Diana, right? So there are two operations. You have to, it's like say you have 100 rows in a file and you have 10 Diana rows. Those 10 rows will be like you have to delete the old file and you have to create a new file by taking this 90 rows, right? So the rewrite operation is nothing but it see parquet is an immutable format. So what it does, it filters for the rows where it is not equal to Diana and get those rows and rewrites in a new file. So that's why you will see again when we see the log for deletes, you will see a remove and add because it removed the old file. See, again this remove is just a yeah, again this remove is just a like it will not physically remove the files unless you do a vacuum, but the stats will help you in tracing that. So you could see a lot of files are removed and again a new files are written because the word Diana is removed from these files. So you could see again the number of rows is 112492. Probably in the input it might be slightly higher for the same partition, say for the Germany, right? It might be slightly higher. So if you see, right, it is around 1 to 5. I mean, it's for USA, but core concept is same. Next, now let's see what are the limitations of partition. So now we know what will happen when we create a partition, when we edit a partition, or when we delete a partition. But the challenge here is it will work only with low cardinality, meaning since a folder is created for every operation, it cannot basically you cannot keep on adding. Say you cannot partition by ID because it will have n number of like 1 million folders will be created, which will affect your storage. For example, in S3 there is a limitation. You cannot list a bunch, lot of files at the same time, right? There will be some thresholds. So the partition folders, right, should be minimal. So that is one of the problem. And second is skewness, right? Because all the partitions, say if Canada is very big compared to other partitions, then it will be again having a issue, right? So let's see how we can fix the first limitation. So that's when, right, the evolution happened and Databricks come up with this reordering technique. Z ordering is nothing but it can be think as like when we like use a zorder command, it will basically rewrite the data and it will optimize or it will remove the small files and create one big file. And when it writes the data, it will keep a id and a name combination nearby. So if id 1 and 2 are basically so it will the queries which will be optimized through GRDRS, a filter which involves these column or an ordering on these columns. So it will collocate the values in this pairs. So each name and ID combination will be stored sequentially in the data. So you can either query based on ID or on name or on both, and it will give the output effectively. Right. So let's run the Z order. So this Z order will basically it's the second evolution of Databricks where they probably improved or removed the issue with the partition, right? So if I query on some other column other than my partition column, it will need to scan everything or it will take some time, right? So instead of that, we are basically doing a co-location or rewriting of the files. So that will locate the IDs and names which are the combinations, right? It will locate nearby. So if I have id1 and id2, then it can basically it will keep id1 name 1, id2 name 2, right, will be nearby. So any query on this combinations will be faster. So after the order you can see the metrics here. So from original 11 files it optimized the content and it removed all the small files and it created 5 new files now. Now let's see, right, what will happen if we see currently we z ordered already. So we are trying to again run a z order, right, on one of the columns. Now this operation should be instantaneous, right, and there are no changes. This is because effectively, right, z order is idempotent, meaning if there is no change in source data, even if you run this query 100 times by any combination of columns, it will not have any impact, right? Now let's okay. Now let's run the same query, right? Earlier it took around 3 seconds. Now we have the order, right? So for a particular name and for a particular set of IC, it took like there is a save of 1 second, right? This is because now it is co-located, so the queries involving those will be quick, right? Now let's see what is the issue with z order, right? Z order is idempotent, but at the same time, right, let's say we rewrite the data, right? So what I'm doing is I'm just triggering an operation where I'm just taking some 10 random rows, I'm inserting again back to the source table, right? Now let us see the metadata again, right? So you will see a data change and it will approximately insert some 10 rows, right? So now, if you see, right, one new file is added, right, and because the 10 rows are inserted. Now, the problem with Z order is basically, see, I have already one 5 files, right? One of the file is holding the Kannada data and which will be very big, right? Now, if I go on again trigger the Z order, since the data has changed, it will do again a rewriting. So it will rewrite again the entire Kannada file because it has to resort, right? So it will do again a global sorting. So meaning it will again has to read both the files, right? And it has to rewrite. Now if you see here, it removed the 2 files and then it created one file because we had 2 files, one original Kannada file and one new file, right? And this is not incremental, right? So it is idempotent, but it is not incremental, meaning uh, far up within a partition, if there is no change in data, it doesn't need to reorder again, right? But if there is some new data added even in a small number, it will again retrigger, right? So it will take a little bit of time, right? So again this is the log. I don't want to go into that. So as we see here, the order, right, it can work on high cardinality column very well. That is good, but it is not incremental, right? Because making a small change again results in rewriting of the 2 files into a single file, right? So that is where Databricks come up with this recent concept known as liquid clustering. Okay, so what they recommend is liquid clustering will solve both the issues. So it will solve skewness and it will solve the low cardinality, high cardinality, and it will also solve. It does an incremental optimize. So it doesn't do one whenever there is a change, it will not rerun for the entire data of that partition, whereas it reruns it only for that incremental data. So it basically internally has a mechanism that will divide the data into cubes or blocks, and it will only change or impact those blocks if a particular size is met. So let's see that in action. So let's see I am creating a liquid clustering, right? So the change to the syntax is you can remove the partition and you can put cluster by country and name, right? Because these are the fields you will query. So again, I'm loading the data. Since there is no partition column, I'm just inserting based on that. Okay, now it has loaded the data. Now let's analyze the table. So what I was saying earlier is to keep an eye on the table properties, right? So you will see same thing, id, name, age, and in terms of partitioning information you will have cluster information, and you will basically see the table properties, and there are quite a lot. So I have copied this. So if you see here, the last time we had just the minimum version and the maximum version, right? Now for liquid clustering to work, see, liquid clustering addresses two different problems. One is your performance problem, skewness problem. The other issue is concurrency, right? In delta tables generally you cannot have two transactions which will write to the same table at the same time. I'll show it at the end. So for overcoming those, delta has come up with two different mechanisms. So one is a decision vectors, so which will be enabled by default on all the liquid clustering table, and another one is the row tracking. So you could see row tracking, right, future, which is enabled. It should have that row tracking. Yeah. So row tracking is supported here, right? So delta dot enable row tracking equal to true. So now let's see how does the metadata files vary. Okay, so let us read the delta log folder. Now, what you see earlier was there was a commit info and then there was a metadata, right? Now we could see more than additionally one more field, right? So we have something known as domain metadata. So this is a critical feature. This will track for each commit which are the IDs which got affected. So let us see that. So let us see after the first commit, right, where we have inserted 100k rows. Let's see what is happening. So if you can see here, we have a new column which is added, right? I think in earlier we don't had the row id column. Now you have a base row id, and you could see the records inserted, the stats is there, and additionally in the domain metadata you will see the watermark. So basically this is the road tracking id. So I will show road tracking id in detail, but it will basically guarantee you as part of this commit what are the IDs which got affected. So in this case we have inserted some 100k rows, so it starts from 0 I believe. So we have till 9999. So now when we do a liquid clustering, it should facilitate both the queries. So you will see a query on the low cardinality columns, right? Like Kannada, this is also coming in a few seconds. Yeah, it comes in around 1 second. And even if you have a query on the name, it will come quickly. So let us even query that. And let me query that. So let us also query on a column, right? The data column. So So earlier I think it took around 3 point some second. Let's see how long it took. Okay, see, I think there is a issue with probably the spelling. Okay, name equal to Alice. So now they should come. See, it reduced from 3 seconds earlier. So it's like a more of a balanced approach. So either you have a low cardinality or a high cardinality. Because of the way it stores internally, it could basically give nominal performance for both sets of queries, right? Now let us update a liquid clustering table, right? So you remember I said the deletion vectors is enabled, right? So when we generally do an update on a partition table, it will do a rewriting. But now when we do a update on liquid clustering table, since it has basically it has the deletion vectors enabled, so you will see a different way of representation in the metadata. So we have now updated the data, right? So earlier we saw there was a remove file and then there was a new operation. We'll see, yeah. When a new row is added, right, like it will see basically now when we do an overwrite, it doesn't need to read the entire data. Rather than that, what it will do is on the older file which was already there, it creates a deletion vector which is like a binary format which will say which of the rows here should not be read. So when it reads this version, it will go and read the file, and it will not read all the data. Instead, it will read only the data which are not deleted. So if you see now, let us do an optimize now. So this liquid clustering is again incremental, so unless it gets to a particular size, even though there are there are some changes happening in the data, you will see it will not do any optimization or rewriting as in z order, right? Now coming back to the deletion vector discussion, so see, we'll again do a delete. This will be more clear. So there are two things which happen during a delete. In a traditional way, you can it will basically needs to read the old file and create a new file rewriting that, right? Whereas in the new method of deletion vectors, it will basically not rewrite the file. Instead of that, it will create a like a watermark or a deletion mark which will say these records in my data is deleted. So since we did a delete, now you will see as part of this latest commit, you will see a deletion vector will be added, right? You will not see complete rewriting of the data. Instead, you will see something known as a deletion vector will be added, right? So if you see here, this operation is relatively quick, right? You will if you see here, earlier when we rewrite the data, it took a long time. But now, since we are just enabling the deletion vectors, it should be relatively faster. Now, let's see where this deletion vector gets stored. So, if we go and see the root folder of my table, you will see deletion vector underscore hash value will be created, which will contain actually, right, in each file what are the rows which are getting deleted. So this way it will basically avoid a complete rewrite, rather it will just store this info. Now let's do one test the incremental refresh, right? So we will insert some 10 random rows into the data, right? And we will again run the liquid clustering. So when you do a optimize again, you will not see any change in files, unlike a z ordering, right? So you could see here nothing has been added or removed, right? Now let's see what is the row tracking. So as I said, right, delta earlier had a limitation with concurrently update, meaning I have two records in my data, right? Say id1 and id2, both are in the same file, right? So if I fire an operation which involves an update to both the records at the same time, it will affect the consistency, right? Let me open an excel. Now let's see how does row tracking helps us in concurrency issue, right? First, let's understand what is the concurrency problem, right? So assume I have a file one.parquet which has two rows ID 1 and 2 with name ABC and EAF. And now let's say we fire a query, right? And first query will update ID 1 with name DEF, right? And this gets committed. Now, when the second query gets the original data, it is having the name ABC, right? But it is trying to update only the row 2, which is having value as DEF, right? But you will see, even though it is trying to update the DEF, after this, when it goes and tries to commit here, you will see that the first row value has been changed, right? Even though it is not the same row which is getting changed, but there is a change, right? So it will corrupt the data. So that's why Databricks prevents concurrency update, or delta prevents the concurrency update. Now, with row id, assume we added a id, like a virtual id for each of the row. With that, what will happen is when the first query fires it will update the zeroth row, and when the second query fires updates the first row. Say this got committed, right? After that, when this commit, or when the delta is trying to commit this one, it knows exactly which rows were affected earlier. So it will handle and recreate a new file such a way that it will get the latest value from the previous commit and also the latest value from the new commit. So that way you will get a stable state. Explaining row tracking. Row tracking is just a feature. When you enable it, you will have an underscore metadata, which is a virtual column. So if you see an underscore metadata in a normal table, right, which is not having a row tracking enabled, right, you will basically see the fields, right? You don't see a field known as row id, okay? But whereas when you query a table which is having the liquid clustering enabled, it will have something known as row id. If you see, right, for each row you could see a row id it is created. How do we basically solve this issue, right? So let me prove the thing that liquid clustering will basically allow concurrent update, right? So let us fire a query where we will update both the tables. First, the liquid clustering table, where we are updating two different values in the data, um, Frank and Grace. I'm making it as a lower case of it, right? So now these two are simultaneous operation. So you will see it has updated, starting update for both the rows in the multiple files parallelly, and you will see this will eventually succeed. Yeah, but let us do the same activity here. Now you will see it will basically fail. Why? Because we are trying to update the same file, right, by two different commits parallelly, so it will fail. So it will eventually fail with the concurrent update exception. So one record got updated. Now the second records, when it tries to update, it has already modified the source file, right? So you will see an concurrent update. So now we could understand with row ID that it has been effectively solved. So as part of this video, we saw the evolutions of indexing, partitioning. It started with partitioning, then it had a Z order for high cardinality values, and eventually partitioning has its own limitation because of skewness, and then Z ordering has its limitation because of it has to rewrite every time when a Z, like whenever there is a small change even. And even with partitioning and Z ordering, you cannot do a concurrent update. Either you have to hard code the partition value, or you will get a error like this. Now, finally, we saw liquid clustering, which stores the data through files, and it will store as blocks with optimized layout, so that it will support both high cardinality queries like name, or low cardinality queries like country, and also at the same time with underlying features like deletion vectors and row tracking, it is able to concurrently update multiple rows without affecting the overall process. So that's all I had have for this video. Thanks for your time. Please do like, share, and subscribe.